Hello again. This is Math 1120 coming to you from the College of DuPage. The title of this lecture is Conservation of Energy and, Power. And I encourage you to be an active learner as you watch this video. Well, we've talked about conservation of energy already, and what we found was, this was our energy theorem, the change in kinetic energy was equal to the total work, and the work can come in different flavors. We can do gravitational potential energy, elastic potential energy, and there can be other kinds of work as well. Now, if you follow and do some algebra on this equation, you end up with this expression saying that the energy before is equal to the energy after, although there can be shifting in where it is, and that is called the conservation of energy master equation. So the work done other is equal to the change in energy, and this is the change in total mechanical energy, which is kinetic, gravitational potential energy, and elastic potential energy. So this equation is important. We'll use this to solve some problems. The work sub other represents the total work done by all forces acting on objects except the force of gravity and the force of the spring. If that's equal to 0, then the total mechanical energy of the system is conserved. If it's greater than 0, then the total mechanical energy of the system increases. And similarly, if it is less than 0, that is W other is less than 0, the total mechanical energy decreases. And it could be, for example, turned into heat energy as an example. Let's do some problems then. So this is talking about sliding down an inclined plane. So here's a block sliding down a distance d of an incline. The incline is called to be frictionless, but this surface is rough, meaning there is friction. So a block is initially at rest on a frictionless plane. It's released and slides down a distance d of the plane. It reaches the bottom of the plane and slides the distance s across a rough horizontal surface until it comes to a stop. So which statement correctly describes the kinetic energy of the block during its trip? A. The kinetic energy of the block increases as it slides down the ramp and remains constant along the horizontal surface. The kinetic energy of the block remains constant as it slides down the ramp and decreases along the horizontal surface, and the kinetic energy of the block increases as it slides down the ramp and decreases along the horizontal surface. I'd probably ask you to pause and cast your vote here, but we're not going to spend time doing that in the video. And the correct solution to this problem that we just read is the mass of the block doesn't change. So the kinetic energy of the block increases when its speed increases and decreases when its speed decreases. Because the block starts from rest at the top of the ramp and its speed increases as it slides down the frictionless incline, the kinetic energy must increase as it slides down the ramp. On the other hand, once the block reaches the horizontal surface, it is traveling with some initial speed, the speed it had when it left the ramp, and then it slows down until it comes to a stop. Because the speed of the block decreases on the horizontal surface, the kinetic energy of the block also decreases. Therefore, the correct answer was C. Here's another problem, this is a home run ball, so the ball is hit with an initial velocity off the bat at an angle. There's a vertical component and there's a horizontal component of the velocity, and we solved a problem like this in a low stakes assessment thing. But now we're being asked to say, oh, can we have a closed form equation for the height of the ball, the maximum height of the projectile? So let's talk about what's going on here, and let's derive this expression using a conservation of energy analysis and discussion. Okay, so here's the setup. There are no non-conservative forces. The work done by gravity is accounted for by the potential energy term. And so we choose a launch point as the initial point and the highest point of the trajectory as the final point. So here's the final point, there's the initial point. We place y equals 0 at the launch point just for convenience to make the calculation easier. And so the kinetic energy changes from an initial kinetic energy of, or excuse me, an additional gravitational potential energy of 0, and it goes up to mgh, where h is unknown. Now we can express the kinetic energy at each point in terms of the velocity, so it's 1/2 mv squared. And so you see what's going to happen here is that, and we know this because these are vectors in the Pythagorean theorem, that the square of the velocity is going to be the square of the square of the magnitude of the velocity is going to be the sum of the squares of the other two things. That's a Pythagorean theorem. And so we have k initial is equal to 1/2 m, and then it is the square of these. And k final is going to be this. So that's kind of the setup. Okay, so what we're going to do then is we're going to say that the conservation of energy tells us that the kinetic energy plus the potential energy is equal to the final kinetic energy plus the final potential energy. So this energy, which was 0 at the outset, is equal to this. Now it turns out that we can simplify this equation. We multiply all the way through by 2 over m, and that'll cancel out the masses, and we'll just have this term involving the sum of the squares of the velocities in the x and y directions is equal to this, plus 2gh. Now, what we know is that at this top part, v final y is equal to 0. And so we can place that equal to 0. And the x component of the acceleration is 0. So the velocity is a constant. So this velocity is equal to the final velocity. And so we can simplify that, subtracting vx squared from both sides and making note of the fact that this is 0. And we get this. The initial velocity in the y direction squared is 2gh, and so we can solve for h. That's the only unknown. And so that is going to be, and the velocity in the y direction, you know, is the initial velocity times the sine of that angle. You see, that's this part here. So it's the sine of that angle. So we have derived that expression. It's useful for you to understand this derivation, and also this is a kind of vector problem that I might ask you someday. Here's another example where we're calculating speed along a vertical circle, and you've seen this before. This is the old skateboard kind of thing. So we have an initial point up here where someone's going, but then they jump on their skateboard and they start going down. So here it's all potential energy, but it starts becoming kinetic energy as you're going down. Okay, so here we tackle a circular motion problem using conservation of energy. Because the acceleration in this problem is not constant, we can't approach it using the tools we studied in circular motion. And actually that's something we skipped anyway. But we can do it using energy considerations. So a boy skateboards down a quarter pipe with radius r is equal to 3 meters. So that is the radius of this quarter pipe. Now, as you're going down, the total mass of the boy in the skateboard is 25 kilograms. So he starts from rest, so there is, and we say there is no friction, and so he starts going down the ramp, and the potential energy will change into kinetic energy. Okay, and so we're supposed to, okay, so we're going to solve this. This is a conservative system. So at the top, the kinetic energy is 0, at the final it's 1/2 mv sub f squared, final velocity. And at the top, it is mg times r. Now the reason it's mg times r is because the distance here is going to be, this has a radius of r, so that means that's how far it has fallen. So that's why it's important that that's a circle. So the height of this thing from here down to here is r. It's the radius of that circle. So it's mgr, and the potential energy at the end is 0, at least relative. So what we're going to do is we're going to set those two things equal. So k1 plus u1 is equal to k initial plus u initial, that's the potential energy, is the kinetic energy final plus the potential energy final. We substitute those things in. The masses can cancel out. There's a 2 there. We know what g is, so we can solve for v sub f. It's going to be the square root of 2g capital R. I plug in all of those numbers and I get that this velocity at the bottom of this is 7.67. Here's another problem. And in this case, what we have is we have to count for both gravitational potential energy and elastic potential energy. Now, in a worst case design scenario, a 2,000 kilogram elevator with a broken cable is falling at 8 meters per second when it first contacts a cushioning spring at the bottom of the shaft. The spring is supposed to stop the elevator and compressing 3 meters as it does so. That would be 10 feet, or more or less 10 feet. As an energy consultant, you're asked to determine what force constant of the spring should be required. How strong of a spring do you need? And we're ignoring air resistance and friction in the elevator guides. Okay. So we take the initial point as the elevator's position when it first contacts the spring. And that is y1 is equal to 3 meters is where it's compressed. So there's the initial point. We're taking that to be 0, and the final point is going to be 3 meters. The elevator's initial speed was v1 was equal to 8 meters per second. So the kinetic energy is 1/2 the mass, 1/2 times 2,000 kilograms times the velocity squared, and that is going to be 64,000 joules. When it stops, the kinetic energy is 0. That means all of that has been turned into potential energy. So the potential energy then is mg, and this is the distance that we've compressed the spring. Now, so that's the change in gravitational potential energy, and then it stops. So you see, this is what is here. Now that means that the and at that final point, the gravitational potential energy is 0. But so what we have is that the elastic potential energy is the change between those two. And so we know what x is. X was this 3 meters. We know, so we substitute that in, and we can use the numbers that we have up here. We're adding those together. So those are the kinetic and potential energies. And the only thing we don't know is K. And we can solve for K. We get K is 2.73 times 10 to the 4th newtons per meter. And you should, mimic these calculations. Make sure that you understand them, and that's a pretty strong spring you need to be a safety thing on an elevator. Okay, we're going to revisit an example that we've looked at earlier, but we're adding a non-conservative force to the system. Okay, so here is, suppose that the glider, and here's a glider that's being used, is initially at rest and the spring is unstretched. You apply a constant force with magnitude 0.610 newtons to the glider. What is the glider speed when it is moved to x is equal to 0.100 meters? Okay, so here's the picture that we get. This is initial, and you see it's attached to a spring. That was the story before, but now we're putting a force this way, so we're stretching the spring out. And so we stretch the spring out, and we go from an initial 0 to a final, which is this, and that's the force, and those are velocities, and so on and so forth. Now, the setup, we should also know, besides the picture, the mechanical energy is not conserved because you've added some work from this external force. But we can still use the energy equations. So what we have is that the kinetic energy initial is equal to 0. The kinetic energy final is equal to this. And we know that the initial is equal to 0 and the final one. Now this is elastic potential energy. You see there's no changing up and down. It's just stretching the spring, and that is going to be 1/2 the spring constant times the extension squared. Okay, and that then is something that you can calculate. There's 1/2, that is the spring constant. They told us that, and that's the distance that is extended. So you see that potential energy is slowing this one down. Okay, so what we can do then is we can solve for the work other, and the work other is going to be this, because we applied that in this direction, in what we're calling the positive x direction. So if we put all these pieces into the equation, this was the kinetic energy plus the potential energy, kinetic energy initial plus potential energy plus other. We substitute everything in, and the only thing that is missing is that we don't know a number for is v sub f. So we can solve for v sub f. You take the square root, and again you should duplicate these things. Now here's some additional considerations. The total mechanical energy changes by amount equal to the work other done by the applied force. So even though it isn't conserved, the energy considerations simplify this problem a great deal. And if this force is removed when the glider reaches that point, at what distance from the starting point does the glider come to rest? And you should, this would be a good problem for you to try to work as well, and there's an answer for you. We now turn our attention to a different concept, which is called power. And you see, time considerations aren't involved directly in the definition of work. They are involved indirectly, however. If you lift a barbell weighing 400 newtons through a vertical distance of 1/2 meter at a constant velocity, you do 200 joules of work on it, whether it takes you 1 hour, 1 second, or a year to do it. Often, however, we need to know how quickly work is done, and the time rate at which work is done or energy is transferred is called power. Like work and energy, power is a scalar quantity. It is not a vector. We define average power as follows. This is the definition of P sub AV, that is average power. When a quantity of work, delta W, is done during a time interval, delta T, the average power, or work per unit time, is defined by P average is equal to delta W over delta T. Now there are units for this, but work comes in joules and time comes in seconds. So you say, oh, it's a joule per second, but we have a name for that. That is named after the famous engineer James Watt, who invented the steam locomotive, and so it is called a watt, W-A-T-T, and that's also often used to be a W, not work, but watt. And a watt is defined to be 1 joule per second. Now remember, it's not a vector, but it can be positive, negative, or zero. And realize it's not the same thing as energy. It's energy per unit time. And so the two cannot be directly interchanged. And we often think about power differently. If someone talked about the power of a car, they'd say, oh, that's a horsepower. And a horsepower is defined in terms of the British unit. So a horsepower is, and work is, distance times force. So horsepower is, this is 550 foot-pounds, where that's the product of the distance, foot, and pound is the unit of force, per second. And that means this is, if you change it to minutes, you would get this. So a 1 horsepower motor running at full load does that much of work every minute. And if you wanted to convert horsepower to watts, this is it. 1 horsepower is equal to 746 watts. And that's the same thing as 0.746 kilowatts. And so if you look at this part of it, you'd say, oh, that means that 1 horsepower equals about 3/4, because that would be 0.75 of a kilowatt. And that's a useful figure to remember for back of the envelope calculations. Now the watt is a familiar unit of electrical power. We will buy 100-watt light bulbs, and that's converting 100 joules of electrical energy into light and heat each second. But there's nothing inherently electrical about a watt. A light bulb could be rated in horsepower, and some automobile manufacturers rate their engines in kilowatts as well as horsepower. Power units can be used to define units of work or energy. For example, when you get your electric bill, it talks about kilowatt hours. Now you see that's taking a kilowatt times time. That makes it into energy. 1 kilowatt hour is the total work done in 1 hour when the power of 1 kilowatt, 10 cubed, joules per second, is applied. So this 1 kilowatt hour is equal to 3.6 megajoules. A kilowatt hour, of course, is a unit of work or energy and not a unit of power. Okay, now when force acts on a moving object, it does work on the object unless the work and displacement are perpendicular. So the power can be expressed in terms of force and velocity in this way. So you see the power is going to be, this is going to be the work done, but that is the force parallel, as we talked about, times delta S divided by delta T. But if I look at, there's the force parallel, but this delta S over delta T is known to be the average velocity. So you see another equation for power is the average power is equal to the force parallel times the average velocity. And here's where we say that. And in fact, if we did this instantaneously with calculus, we would have this equation. It's a curious fact of modern life that although energy is an abstract physical quantity, we buy and sell it. That's what electrical utilities do. We don't buy a newton of force or a meter per second of velocity, but a kilowatt hour is the same thing. This is what it usually costs, depending on who you're buying your power from. Let's look at another example. A jet airplane engine develops a forward force on the plane of 15,000 newtons, and that's this many pounds. When the plane is flying at 300 meters per second, and that's roughly 670 miles per hour, that is a speed that a plane might fly at, what horsepower does the engine develop? Okay. Well, this is the setup then. The power is equal to F times V. V is a constant, 300 meters, and that is the force of the thrust. So that is the power in watts. But we have to change watts into horsepower to comply with the problem, and so we take watts times 1 horsepower per 746 watts. The watts will cancel one with another. Our answer will be horsepower, and so it is 6,000 horsepower. And here's another practice problem if you want to do some more work to make sure you understand the concept. Here's a final example. Maybe it's not final, another example I guess I'll say. And this is a marathon stair climb. Okay, so a runner has to start running upstairs. Let's just say in the Willis Tower. They're talking about that Willis Tower run. And the rate at which she does this is directly related to her average power output. Now, as part of a charity run then, a Chicago marathon runner with a mass of this runs up the stairs to the top of the Willis Tower, the tallest building in Chicago, still the tallest building in Chicago, in 15 minutes. They're really moving pretty fast. What is her average power output in watts, in kilowatts, and in horsepower? So we're changing those things. Well, here's a setup then. So what happens is the work that this runner is doing is they're changing their the kinetic energy is being changed into potential energy. So the work they're doing is they have to take their mass, work against the acceleration due to gravity for the height. And this is the height of the Willis Tower in meters. They're working against the acceleration due to gravity, and that is their mass. So this is how many joules of work this runner must do. So that's the work. So you take the work divided by 15 minutes is 900 seconds. So this is going to be joules per second. You do the calculation carefully, and you get that this is 241 watts. And we have to change the watts to horsepower as we did in the previous problem. And so we'll get 0.323 horsepower for this marathon runner. And here's a practice problem for you. Here's a concept problem. So a baseball is dropped from a tall building. Which of the following statements is true regarding the power delivered to the baseball by the gravitational force? The power is constant in time as the ball falls, the power decreases in time as the ball falls, or the power increases in time as the ball falls. Now, as I said, I will not be asking you questions like this usually because I'm not a fan of multiple choice things, but on your certification exams, often you will find multiple choice tests. Okay, so here's the answer. Since the power can be written as P is equal to F times V, the correct answer must be C. You see, the gravitational force, G, remains constant as the ball falls, but its speed increases in accord with the free fall equations we learned later. The ball is going faster after you drop it and when it hits the ground. So the correct answer must be C. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.